In this lecture video, we move into the next module on the Latin square design. Now let's first look at the model for the Latin square design. And so we'll first look at the means model representation of the design. So the statistical model for the Latin square design, to evaluate the effects of a number of treatments, which we'll denote by P, can be written in the following way using the means model representation. So y sub ij and then a k in, I've got square brackets here, some authors use parentheses. And I'll explain that kind of different notation here in a second. All right, but that's equal to rho sub I plus gamma sub j plus mu sub k plus epsilon ij. Now I ranges from 1 up to p, j also ranges from 1 up to p, k is some integer between 1 and p, and is determined functionally by the combination of I and j. So we can think of the ordered pair I comma j as determining the particular value of lowercase k. Now that is why in this notation here on the response variable y sub ij, we have appended to the subscript the k inside either square brackets or parentheses, depending upon the author you look at. And because k is determined, functionally determined by I and j, it's really unnecessary to include that in the subscript on the response. Now, something is certainly required as a subscript on the mu here, either a k, or we could have an I and a j there as well, but having a k here and then just making the statement that k depends on I and j is perhaps a little bit more obvious in terms of what this represents. But the bottom line here is that in this particular model, the value of k is determined by the values of I and j. Now, what I'm going to do is to denote this functional relationship or this functional dependence of k, lowercase k, on the ordered pair, I comma j, by the following notation. So what this says here is that lowercase k, which is this integer that varies from 1 to p, and which depends on I and j, is given by or equal to this function, capital K, evaluated at the ordered pair I comma j. And so we'll use that in the subsequent description. Now, the model components are as follows. Y sub ij, and then with k in brackets, is the response measured on the experimental unit in row I and column j of the Latin square. And that particular cell of the Latin square has been assigned the treatment given by little k equal to capital K evaluated at I and j. So in other words, this is just a kind of a mathematical way of saying that a particular cell in the Latin square, and we'll see a schematic of this here in a few minutes, but a Latin square is a square. It's a square table or a square matrix. It's a P by P matrix or a P by P table, and so it has P times P or P squared cells in that matrix or table, and associated with each cell, each location, I comma j, I being the row, j being the column, then to each cell there is assigned a treatment, and it's done in a particular way that really defines the Latin square itself. And so again, this is just a mathematical way of indicating or expressing the fact that the treatment number or the identifier for that treatment depends on the row and the column in that table. Now, looking at the expression on the right-hand side of the equality, rho sub I is the effect of the ith row on the response, so the row of the table, or the ith row of the square. Gamma sub j is the additive effect of the jth column on the response. Mu sub k is the population mean treatment response under treatment k. And then epsilon sub ij is the random error associated with the experimental unit in, I say receiving here, that's a typo, I'll have to fix that, but unit in row I and column J that is receiving treatment K, which is determined by the particular row I and the particular column J. Now we can also express the statistical model for the Latin square design using an effects model. And in doing that, we essentially decompose the population treatment mean, mu sub k, into the sum of two components, mu and tau sub k. And so most everything here in the effects model, the effects form of the model, is the same, except we have a mu here and a tau sub k. And if we look and see what these represent, this should be fairly familiar from what we've already done in the randomized complete block design. So mu is the overall population mean response across all treatments, and tau sub k is the treatment effect of treatment k. Everything else in the model has the same meaning and the same interpretation. Now let's look at the assumptions associated with the statistical model for the Latin square design. First of all, the row and the column effects are considered to be and treated as random effects, just as in the randomized complete block design. In the randomized complete block design, remember that we were accounting for one extraneous source of variability, and that source of variability was treated as a random effect. Now, in the Latin square design model, the Latin square is essentially designed to account for two extraneous sources of variation. So we have these two sources that we include in the model. We can think of them as two blocking factors, rho and gamma. So the rho effects are random variables. They are independent random variables with mean 0 and a variance that is denoted by sigma squared sub rho. And if we need to perform inferences on these, we would assume that they are normally distributed. The column effects, the gammas, gamma sub j's, are independent random variables. We assume they are normally distributed. They have a mean of 0 and a variance that is unknown, but denoted by sigma squared sub gamma. And then we have the model error terms, the epsilon sub ij's. As is always the case, those are independent random variables with a mean of 0 and a variance which we'll denote by sigma squared. And we will assume that they are normally distributed. In addition, these three sets of random variables, the row effects, the column effects, and the model error terms, are all stochastically independent of each other. So that's the assumption that is made and that is imposed on the statistical model. Now, the population treatment means, the mu sub k's, or if we are dealing with the effects model, the treatment effects, the tau sub k's, can be either fixed effects or random effects, as was the case for the completely randomized design and also the randomized complete block design. If the treatment effects or the population treatment means are fixed effects, then these are unknown constants that need to be estimated, and we would make inferences about them via hypothesis testing and so forth. If we are thinking about the effects model, where the tau sub k's would be equal to the difference between the population treatment mean mu sub k and the overall average of the treatment means, then the assumption, then based on this assumption, and the way that we parameterize things in doing this, the sum of the tau sub k's would be equal to 0. Now, on the other hand, if the treatment effect is considered to be random, right, then the mu sub k's or the tau sub k's, if we're thinking about the effects model, would be random variables. In particular, under the means model parameterization, the mu sub k's would be random variables with a mean of mu, which is the overall population mean, treatment mean, and a variance of sigma tau squared, and we would assume that they are normally distributed. If we are thinking in terms of the effects model, then the tau sub k's would have a mean of 0, a variance that is denoted by sigma squared sub tau, and again, if needed, if distributional assumptions are made, we would the standard assumption is to assume that those are normally distributed. Now let's look at the advantages, disadvantages, and uses of the Latin square design. So there's basically one primary advantage and one primary use. The use is the advantage is the same as the use. We do have a kind of a secondary advantage here, but the first advantage is that the Latin square design allows the experimenter to control for two extraneous sources of variation. And so you'll remember back with the randomized complete block design, the reason we looked at that is because it allowed us to account for one extraneous source of variation. And so when we account for that one extraneous source of variation in terms of how we randomize, and also in terms of the statistical model, then we are able to estimate differences between treatment effects more precisely. We are able to test hypotheses, comparing population treatment means with greater power. And the reason we're able to do that is because by virtue of the randomization of the RCB and the fact that we have the blocking factor in the model accounting for that extraneous source of variation, that blocking term, that random effect for the blocks, is taking out variability due to blocks from the experimental error. All right, and so that gives us a smaller estimate of the variability associated with experimental error, and that leads to greater precision in terms of our estimates and more power in terms of our hypothesis tests. Now, in some situations, there is more than one identifiable source of extraneous variation, and when the number of sources of extraneous variability is 2, then we can potentially use the Latin square design to account for both sources of extraneous variation. And so in doing that, both in the randomization, but also in the statistical model, then we would be able to, again, remove that extraneous variation from the error term and thereby get even greater power and greater precision. Now, one additional characteristic of the Latin square design is that, and we would consider this to be an advantage, is that if we need to increase the number of replications, we can add additional Latin squares. So additional Latin squares can be added to an experiment as needed to increase the number of replications. And in doing this, that really does not complicate the analysis that much at all. Now, what are some of the disadvantages? Well, there's a certain structure to the Latin square design such that the number of treatments, which we're denoting by P here, is the same as the number of rows and number of columns in the Latin square. And so the implication of that is, in order to perform an experiment using a Latin square design where we're studying P treatments, that requires P squared experimental units for each square. And so the number of experimental units increases quadratically with the number of treatments when we're using a Latin square design. So the size of the experiment increases very quickly as the number of treatments increases. As the number of treatments increases, the variance of the experimental error tends to increase as well, because as we get more and more experimental material that we're using in the experiment, the less homogeneous the experimental material tends to become or to be, and so that has the effect of increasing the variability associated with the experimental error term. Now, one other advantage or disadvantage is that the number of degrees of freedom for error is small when the number of treatments is small. On the other hand, going back to the first, if we have a larger number of treatments, then the number of experimental units gets quite large. And then finally, the analysis is very complicated if there are missing values, or if the treatments are not assigned according to the randomization. All right, so if the treatments are misapplied or misaligned due to an error in either the randomization, how the schedule is produced, or just in terms of how a good randomization, if it's misapplied in terms of applying those assigned treatments to the experimental units, then that really complicates the analysis. All right, so what are the primary uses of the Latin square design? Well, as we said a few minutes ago, there's one primary use, one primary advantage, and that is that the Latin square design is used primarily to remove two extraneous sources of variation from the experimental error. This obviously is a very important thing to do whenever we are performing an experiment, planning an experiment to be performed, planning it, designing it, organizing it in such a way that we get as much bang for the buck, as much information per unit observation as possible. Right? We want to perform the experiment in such a way we're going to be expending time, money, and other resources to perform the experiment, and we want to be able to make conclusions that are as strong as possible. Right? That means testing hypotheses with as much power as possible, computing point estimates that are as reliable as possible, and also constructing confidence intervals that are as precise as possible. And so it becomes very important to design an experiment in such a way that you get as much information as possible from each observation, and you're performing the experiment so that if there are these extraneous sources of variability, when it comes to the analysis, you have the ability to filter that extraneous variability out. And we saw that that is the case when we have a randomized complete block design. We're able to do that by randomizing in accordance with the blocking principles, the randomized complete block design principles. We are able to compare treatments within blocks. And by doing that, we filter out that block-to-block variability. When there are two identifiable sources of extraneous variation in an experimental situation, whether it would be in an agricultural field or in a lab setting, in some kind of an animal science setting, in a healthcare setting, if there are two identifiable sources of extraneous variation, then it may be possible to perform the experiment using a Latin square design in such a way that treatment comparisons can be made that filter out both sources of variability and thereby providing more power to comparisons and precision in computing estimates of treatment differences and so forth. So we're beginning to see these more complicated designs, and the reason these designs exist, one reason is to provide statistical efficiencies. Some designs exist for logistical reasons. In some situations, it's more convenient to use certain designs. In some situations, it may be almost impossible to perform certain designs, but easier to use other designs. In this particular situation, in both the randomized block and the Latin square design situation, these models exist primarily for the purpose of providing increasing statistical efficiencies. Now let's look at the canonical layout for the Latin square design. So consider a Latin square design to evaluate and compare 4 treatments. This is going to require a square with 4 rows and 4 columns. Denote the 4 treatments using the letters A, B, C, and D. With that, the canonical layout for the 4x4 Latin square is given below. So you can see here I've got my 4x4 table, my 4x4 square or matrix, however you want to think about that. And in the rows, I've got these labeled 1, 2, 3, 4. These are my row blocking factors. And for the columns, I've got my column blocking factors, which again I'm labeling 1, 2, 3, and 4. And so in order to do or have a Latin square design, the number of row blocking factors and the number of column blocking factors both have to be equal to each other, but also to the number of treatments. And so that is a restriction on the scenarios to which the Latin square design could be applied. But there are many situations where it's not a problem for these things to line up in this way or to match in this way. Now, to construct the initial layout, this canonical or initial layout, start off by listing the treatments in order. So A, B, C, D in the first row. So that's what I've got here, the first row. I'm listing them in order, alphabetical order. All right. And then for each subsequent row, shift the letters from the immediately preceding row one column to the left. And so to get the values or the initial treatment listing for the second row, we would look at what's in the first row and then shift everything to the left one cell. And the one on the very left, that would wrap around to the right. And so B in the first row, B is in the second column, it goes to the first column in row 2. In the first row, C is in the third column. That would go to the second column in row 2. And then finally, D in the first row is in column 4 in row 2. That would be in the third column. And because A is in the first column in row 1, in the second column it wraps around to column 4. Then to get the canonical structure for the third row, this is what we start off with initially. Again, we're going to do the same kind of process. We look to the immediately preceding row. All right, and we shift everything to the left one cell. For the first one, that wraps around to the last. All right, and so we get C, D, A, B for row 3. And then finally, we do the same thing for the fourth row, looking at the third row and shifting everything one cell, one column to the left. So we have D, A, B, C. So that's the initial layout, the canonical representation for the Latin square design. And again, the A, B, C, and D represent the levels of the 4 treatments, whatever those 4 treatments might happen to be. Now let's look at the randomization for the Latin square design. So here are the steps for producing a randomization for a Latin square. The first step, step 1, obtain the initial canonical layout for the square. Well, that's the layout that we just looked at. The second step is to randomize the rows and then to rearrange them accordingly. Once we've done that, the next step is to randomize the columns and to rearrange the columns accordingly. Once we've done these steps, the square has been randomized and the treatments are assigned to the experimental units corresponding to the cells in the physical square itself. So let's take a look. The first step, and we'll use this same situation where we have 4 treatments. So we've got a 4x4 Latin square. Here is the initial canonical layout for the square. So the first row has the treatments assigned, or the treatments listed A, B, C, D. The second row has them listed B, C, D, A. The third row C, D, A, B. The fourth row D, A, B, C. All right, so that's the first step. The second step is to randomize the rows and to rearrange the rows accordingly. And so there are a variety of ways that you could do that. You could put 4 slips of paper labeled 1, 2, 3, and 4 into a hat, mix them up, pull one out, write it down without putting it back in. You select the next one out and so forth until you've done that for all 4 rows. I actually created this randomization using the TI-84 calculator, but you could use SAS, you could use R, you could use SPSS, or any language really that has the capability to produce pseudo-random numbers. All right, and so this is the randomization that I got for the rows, and notice that I've already, in going to this slide, I've already rearranged the rows according to that randomization. So let me go back one slide. Okay, there's what it was before. That's the initial canonical representation. Now I'm going to rearrange the rows according to the row randomization. So row 3 gets moved up to the first row. Row 4 gets moved up to the second row. Row 1 gets moved down to the third row. And then row 2 gets moved down to the fourth row. And so that is what that looks like. So we've randomized the rows. Now, the next step is to randomize the columns. All right, now I also used my TI-84 all right, to come up with a column randomization, and this is the randomization that it came up with. And so with this, what we're going to do is we're going to move column 4 into the first position. Column 2 stays in its position. Column 1 moves to the third position, the third column, and then column 3 moves over to the last column. And so when we do that, then this is what we have here. So we have randomized our Latin square. And so then once we've done that, we would assign these treatments to the experimental units corresponding to the cells in the physical square. So notice that in this representation of the table, or the square, now what I'm listing the rows and columns I'm listing the actual physical rows and the physical columns. Okay, and so going to that, so the cell, so if we think about the actual experimental units, the 1-1 experimental unit gets treatment B, the 1-2 unit gets treatment D, the 1-3 unit gets treatment C, the 1-4 unit gets treatment A. All right, then the 2-1 experimental unit gets treatment C, the 2-2 unit gets treatment A, the 2-3 unit gets treatment D, and the 2-4 unit gets treatment B, and so forth. Now let me just stop here for a minute and say that the actual organization or layout of the experimental units does not have to be a physical square. We just need to be able to logically organize the units in this fashion, right, in thinking about the two sources of extraneous variation, what we're calling the row blocking factor and the column blocking factor. We need to be able to schematically represent them this way so that we can come up with the initial canonical layout and then do the randomization. But again, the actual physical locations of the experimental units may not be a physical square, but they can at least be addressed or identified in a way as we've done here. So I think this is a good place to stop this video. In the next video, we will look at analysis of data from the Latin square design.